Let's work the following example where we need to compute the net electric field at a particular location in space due to two source charges. We will choose a specific Cartesian coordinate system and express all vector quantities in terms of components referenced to that coordinate system. Here's the problem. Find the total electric field E net at position O due to charges Q1 and Q2. Both the values of charges Q1 and Q2, as well as the position vectors R sub O, R1, R2 that locate, respectively, the observation location O, charge 1, and charge 2 are given as shown. Here's our approach. We will compute the electric field due to each point charge at location O. Then we will use superposition, which tells us that the total electric field E net at O is just the vector sum of the electric fields due to all of the point charges. Let's start by ignoring Q2 completely and focus solely on finding the electric field due to Q1. To calculate this, we need the relative position vector R sub 1L that points from Q1, the source of the field, to observation location O. That's given by the vector subtraction R sub O minus R1. We also need to compute the magnitude of R sub 1 rel and the unit vector R sub 1 rel hat. With those quantities in hand, we can now compute E1, the electric field at location O due to Q1. Let's do a quick sanity check of this answer. Since Q1 is positive, then we expect the components of E1 to have the same sign as the unit vector R sub 1 rel hat, because the E field for a positive point charge points radially outward away from the source charge, that is, in the direction of R sub 1 rel hat in this case. That's what we have, so that gives us some confidence that our answer is correct. Now let's ignore Q1 completely and focus solely on finding the electric field due to Q2. To calculate this, we need the relative position vector R sub 2 rel that points from Q2, the source of the field due to Q2, to location O. That's given by the vector subtraction R sub O minus R2. We also need to compute the magnitude and the unit vector for R sub 2 rel. Now with these quantities in hand, we can now compute E2, the electric field at location O due to Q2. Let's do a quick check of this answer too. Since Q2 is negative, then we expect the components of E2 to have the opposite signs as the components of the unit vector R sub 2 rel, because the E field for a negative point charge points radially inward toward the source charge. That is, in this case, opposite to the direction of R sub 2 rel hat. That's what we have, so that's good too. Now these kinds of quick checks don't guarantee that our answers are correct, but at least we can test to see if our answers are obviously wrong, so that's helpful. Now for the final step. We add up all of the electric fields to get the total, the net electric field at location O. We see that by sketching arrows to represent E1 and E2, that when we add these arrows graphically, we obtain an arrow representing the net electric field, E net, and we see that this arrow representing E net is consistent with our numerical result. It's sometimes a little tricky to draw the sketches, especially in three spatial dimensions, like this problem, but it's always a good idea to make a sketch whenever possible to help us visualize the problem so we can check to see if our numerical answers make sense.